In this video, we will implement WGAN and WGAN with gradient penalty. And let me just show you an example of why we should care about this. Here is training on MNIST with no batch norm, but with WGAN loss. And here is training on MNIST with no batch norm, but with normal GAN loss. Let's start off with the pros of WGAN. And the primary pro is that we have better training stability. And if you've played around with hyperparameters and training the original GAN or DC GAN, then you know that this is, a really, really great thing. The other pro is that the loss actually means something for WGAN. And it kind of gives us a termination criteria. Now, this is very different from the previous GANs that we've seen, where the loss really told us nothing, and they just spiked around. When one improved, the other got worse, and vice versa. But more on those later. The con of WGAN is that it takes longer to train, but really there's a question mark here because it might take longer to train, but since it's better training stability, you'll spend less time just playing around with hyperparameters. So let me just bring up one point about better training stability. So one thing, if you've trained a lot of GANs, you might notice that you get outputs that look something like this. If we're training MNIST, where the network is only outputting a single digit, so in this case 1, or it might output just 2 digits like 1 and 9 or something. And the problem here is something called mode collapse. And this is essentially when the model has collapsed to only output specific classes. And this is something that WGAN prevents. But to try to understand WGAN, let's first recap, GANs that we've seen so far. So the idea in GANs is that we have two probability distributions, PG and PR, where PG is the distribution that comes out from the generator. And this is sort of an implicit distribution because we send in some latent noise vector, SED, and we get out some probability distribution. So the noise goes through some network in the generator, and then the output from that is some probability distribution. Then we have PR, which is a distribution from the real images. And what we want is for these distributions, PG and PR, to be very similar. And when we've succeeded in that, we are generating realistic looking images. So let's just say we have two probability distributions, PG and PR, and we visualize them like this. Our goal is then to move this PG distribution to get closer to the PR, because then we're generating more realistic looking images. So the real issue here is how we define distance, and more specifically, how we define distance between two probability distributions, PG and PR. There exists some common ways from statistics. One of them is the Kullback-Leibler or KL divergence. Then we have Jensen-Shannon, JS divergence, or one other is Wasserstein distance. And the one that we've used so far, the GAN loss that we've used with logarithms and so on, is equivalent to this JS divergence. And sort of the very quick summary, very overview is that JS divergence has gradient issues leading to unstable training, and WGAN instead changes the basis from its loss to Wasserstein distance. So, in the paper, they do a lot of math, like really a lot of math. And if you want to get more into the theory and the maths behind WGAN, I recommend first reading through this blog post by Alexander Irpan, which was sort of insightful, and then you can sort of go through the paper. So, they do a lot of math. All right, so what do we actually get for the results from WGAN? Drum roll, please. And what we get is this expression right here. So here we have that x comes from some real probability distribution, so x is just a real image, and then we take f of that x, and then f in this case is the discriminator, but they've actually changed the name from discriminator to critic in this paper. And the reason is that they no longer uses a sigmoid at the end of the discriminator, which doesn't limit the output to be between 0 and 1. And over here, they then take x from some p of theta, which is just that they generate some image. So they send in some latent noise to the generator, and then what's output they just call x. And then they take the critic, in this case, of x, where x is some generated image. But we have one additional thing, which is this constraint right here on the discriminator, which is that the function needs to be one Lipschitz continuous. And I won't go into more depth on what that actually means, but essentially what it means is that we need the norm of the gradient of f to be less than or equal to 1. But more concretely, what we get is that we have this expression right here, and we now have a very similar thing to what we've seen previously, where we have this game where the discriminator wants to, in this case, separate these two as much as possible because it wants to be able to distinguish them. So that means to maximize this expression. But the generator, on the other hand, wants to put these closer to each other. In other words, it wants to minimize this expression. So one thing that's very nice that I mentioned in the beginning is that we now have a sort of termination criteria, which is that in the end of training, the discriminator, if the generator has done a good job, the discriminator will not be able to distinguish between fake and real. And what that means is that it will need to guess with a probability of 0.5, which is real and which is fake. And so if you just think about it, after some time, this expression right here, when the discriminator wants to maximize this, it will actually go to 0 because there will be no difference between the fake images, so taking x from this theta distribution, probability distribution, and taking x from this real distribution. And that is something that they talk about in the paper, that they empirically were able to get results where when the discriminator converged to 0, that was actually correlated with good quality images. So this is the paper. It's going to be linked in the video description, Wasserstein GAN. So I'm not going to go through the paper, but what we're going to actually do is just look at the implementation details. So in the WGAN paper, they actually summarize what we need to do for training, the implementation details very nicely. So they used a learning rate alpha of 5e minus 5. They used a C of 0.01, and I'm going to go through what that is just in a little bit. Then they used a batch size of 64, and then n critic to be 5. So those will make more sense when I actually go through it below here. So they say while theta has not converged, and we now know that we can have a metric for when it has converged, meaning when the critic's loss is going very close to 0. After that, they do a for loop for the value in number of critic. And what this is about is that it trains the critic more than the generator. So, more concretely, for every 5 update steps for the critic, we have 1 update step for the generator. Then inside here, there's really not that big of a difference from what we've done previously in GANs. They just sort of compute the gradient of this, and they want to maximize it. So they do plus instead of subtraction when we want to actually minimize. They times this learning rate times the gradient, which in this case, they use the optimizer RMS prop instead of atom. So what's interesting here is that they do this clipping. So that's the parameter C that I talked about in the beginning of 0.01. What they do is that they clip every weight parameter in the network to be between minus, in this case, 0.01 and 0.01. And remember that we had this constraint that the function or the critic has to be one Lipschitz continuous. And so one way they found to enforce this constraint is by clipping the weight parameters to be within a small range, in this case of 0.01. After that, they train the generator, so they sample some latent noise, and then they compute sort of the gradient of this expression with respect to the theta parameters. And then they do the update step with taking the parameters theta minus, since we want to minimize, alpha times RMS prop. So also this right here, empirical results of the paper, they show 2 main benefits, which is that they now have a meaningful loss metrics that correlates with generators convergence and sample quality. And then, as I talked about, improved stability. Okay, so for the code, we're going to base everything off of our DC GAN implementation that we did in the last video. So pretty much everything is going to be the same. We're just going to do some modifications to this to adapt it to WGAN. So we're going to use the exact same model, which we implemented in the last video. And the thing we want to do now is just change the training setup. All right, so first of all, the learning rate should be 5e minus 5. The batch size should be 64. I don't know if they actually said what the latent, the Z dimension should be, but let's keep it to 100. And then num epochs, 5 is okay. We'll use the same number of features in the discriminating generator. Now we need to take two more. So we need to take critic iterations and then await clip. So this is the parameter C that we had in the paper, and it's going to be 0.01. Everything here looks all right. And what we're going to do here is we're going to modify the optimizer to now use RMS prop instead. So for that, we can then remove these beta values and also modify this one to RMS prop. For WGAN, we're not using BC loss. BC loss had these logarithms and stuff, so we don't need to use this anymore. We can just remove it. Everything here looks all right. We don't need to modify anything here. One thing we can do is change the name of the discriminator. We can just keep this as discriminator because we implemented that in the previous video, but the name is now actually the critic. So for the actual training, let's see what we need to modify here. So what we need to add here is that we want to train the critic more. So we're going to have a for loop for underscore in range of critic iterations. And then let's copy paste in that noise and the fake generation. So a lot of this is going to be similar to what we did previously. We have that fake image, but we're going to now do critic real to be critic on real, and then dot reshape to be minus just into a flat vector. Critic fake, we're going to do the critic on fake dot reshape -1, and then the loss of the critic is going to be sort of torch mean, that's the expected value, on critic real, and then subtracted with torch mean of critic fake. That's sort of exactly following the formula that we saw in the slides. One thing here is that these algorithms in RMS prop are meant to minimize something. So we want to maximize this according to sort of the paper, but these optimization algorithms are for minimizing. So what we can do is we can just use the trick that maximizing is the same as minimizing the negative of that. So we'll just take the negative of that, and then we'll do critic.0grad. We'll do loss critic dot backward, and then we got to do retain graph equals true. And why we need to do retain graph equals true here is because we're going to reutilize sort of these computation for fake when we do the update step for the generator. And this should be loss underscore critic and then opt critic dot step. And I'm not sure if I actually changed the name of that. So this right here should be opt critic. This should also be critic dot parameters. And then just one more thing is that we're going to go through the parameters. So for p in critic parameters, we're going to do parameter.data.clamp. And this underscore is that it's done in place. And then we're going to do minus wait clip to wait clip. So remember, when we now sort of train the generator, we want to minimize E of critic of some generated fake. So let's just do output equals critic of fake and then dot reshape -1. We're going to do calculate the loss to be minus torch dot mean of this output. And then we just got to do the update step. So gen 0 grad loss gen dot backward and opt gen dot step. All right, so let's remove all of those previous lines right here. And we're going to keep this for printing to TensorBoard. All right, so hopefully this works now. Let's actually take the image folder with the celebrity dataset, and we can use that to make sure that it works. So let's just comment that eminence dataset, and then we need to change the channel dimension to be 3, and let's see if this runs. All right, and we get an error here. We need to do critic because we changed the name. So let's try and rerun it, and hopefully it works. All right, and we've got to do here critic.train and loss discriminator. We need to change this to loss critic, and hopefully that's the last thing. So after a couple of iterations, I see that it's not training it at all, And that's because there's an error in the model. Remember that I said that the discriminator no longer outputs a value between 0 and 1, and that's because it doesn't have the sigmoid activation function at the end. And really, we should, change this name to critic because of that. But let's just have it as discriminator for now. So let's retrain it, and hopefully this works. All right, so, we can see right here that it's definitely converging to something. It needs a lot more training, but at least it's working. So I think I don't want to train this for too long. So let's stop training right there. And then one thing they mention in the paper is that weight clipping is a clearly terrible way to enforce Lipschitz constraint. If the clipping parameter is large, then it can take a long time for any weight to reach the limit, thereby making it harder to train the critic to optimality. If the clipping is small, this can easily lead to vanishing gradients when the number of layers is big or batch normalization is not used. So this leads us to WGAN-GP. So the paper is Improved Training of Wasserstein GANs, and I'm going to put a link to it in the video description if you want to check it out. But really, this paper is all about having a better way of enforcing the Lipschitz constraint. And so let's jump into the details of the implementation. So this paper also has a nice summary of the WGAN with gradient penalty implementation. So the WGAN-GP, the GP stands for gradient penalty. Just quickly, let's go through some of the details. They use a lambda of 10. They use number of critic to 5, similar as the last paper, having a ratio of 5:1, so 5 critic updates and then 1 generator update. They use a learning rate of 1e minus 4, so they use the atom optimizer with the beta 1 of 0, so they completely remove the momentum term, if you're familiar with atom. Otherwise, we just use beta 1 equals 0 and beta 2 equals 0.9. So how they change training of the critic is that they sort of generate x tilde from the generator, having some latent noise vector. And then on this line right here, they take an interpolation between a real image and a generated image. And they do this using a random number epsilon that's between 0 and 1. So in the paper, they have some theory backing up that if they take this interpolated image x hat, and they take the norm of the gradient of that interpolation, then they can satisfy this Lipschitz constraint. So specifically what they do here is that they take the norm, so they add this term to the loss function, and so they take this lambda parameter, which they set to 10 right here, so just a regularization parameter, essentially. Then they take the norm of that gradient with respect to that x hat, and then they subtract 1 and take that squared. So the idea here is that the norm of the gradient is going to be close to 1, and that will enforce the Lipschitz constraint. And then the update for the generator is essentially the same. The only difference is how they enforce this Lipschitz constraint. Instead of clipping the parameters to be within a small range, they now do this, which is a much nicer way of doing it, since we're not limiting the weights of the generator or the weights of the critic in any way. So what we're going to do is we're going to create another file. We're going to call it utils. And in this file, and then inside this one, we're going to import torch. We're going to import torch.nn as nn. And what we want to do here is just define this gradient penalty function, which is going to take as input the critic, some real images, some fake ones, and then just the device. We can set a default to CPU. And so we want to have the batch size, number of channels, height, and width. And that's going to be just real.shape. And then we're going to create these epsilon values. That's going to be uniform from 0 to 1. And we gotta do that for every of our examples. So we're going to do epsilon to be torch.rand of batch size, comma 1, comma 1, comma 1. And so we only want one epsilon value for each example, but we're going to use 111 because we're going to then repeat just 1 for that dimension, but then we gotta repeat it for the number of channels, the height and the width, and then to device. And this is for creating the interpolated images. So the interpolated images are just going to be real times this epsilon. And then, so let's say epsilon is 0.01 or 0.1. Then it's going to take 10% of the real image, and it's going to take plus fake times 1 minus epsilon. So it's going to be, in this case, an interpolation of 90% of that fake image and 10% of the real one. But of course, these are random, so it's going to be sort of randomized to be any value between 0 and 1. And then we want to calculate the critic scores. So we're going to do mixed scores is going to be critic of interpolated images. And so we call it mixed scores because these are the scores from the interpolated images. Then to calculate the gradient, we're going to do gradient is torch.autograd.grad. And we're going to compute the gradients. So the inputs are going to be the interpolated images, and the outputs are going to be the mixed scores. And then we got to specify grad outputs, which size they should be, and then they're going to be torch ones like mixed scores. And we also got to do create graph equals true, and then retain graph equals true. All right, so, and then we got to take this, the first element of those. So what we're really doing here is we're computing the gradient of the mixed scores with respect to the interpolated images. So now that we have that gradient, we're going to just do gradient.view. And so we're going to flatten this. So we're going to do gradient of view.shape of 0 and then -1. And here we're just doing, so gradient shape of 0 is just the number of examples. And then we want to flatten all the other dimensions. And that is because we want to take the norm. So gradient norm is just gradient.norm of 2 and then dimension 1. So we're taking the norm across that dimension that we just flattened. And then the gradient penalty is going to be torch mean of gradient norm -1 and that thing squared. So this is just from what they did in the paper. And then we want to return the gradient penalty. Okay, so moving on to sort of the model. One thing they did in the model was that instead of using batch norm for the discriminator, or the critic, sorry, that's the correct term, they used instance norm. So I'm not, in the paper they say that they use layer norm, but I guess layer norm and instance norm is quite similar. So I'm just going to use instance norm instead. And the only thing really we want here is that it doesn't normalize across the batches. Okay, so for the training, we need to change, first of all, the learning rate. So it's going to be 1e-4. They use the batch size of 64. I think everything is pretty similar here, except that now we're just going to, remove the weight clipping. And then also from utils, we got to import gradient penalty. One more thing we got to do also is the lambda for the gradient penalty, and that was set to 10 in the paper. Next, for the, let's see, the optimizer, they used Atom. So let's change back to Atom. Then they used betas to be 0.00 and then 0.9. So we're just going to do that for both. Betas equals 0.0, 0.9. And then in the training right here, if we go down here, we need to add this gradient penalty. So I guess what we can do is we can do GP equals gradient penalty, and we gotta send in the critic, the real, and the fake. And then let's set device equals device so that it runs on CUDA. And then let's see here. So let's just do it like this so we can have it on multiple lines. Then we're gonna have plus lambda GP times GP, and then let's close that like that. All right, so that what we're doing here is we have the original loss that we trained for WGAN, and all we're adding is this lambda times the gradient penalty that was computed inside that gradient penalty function. And that's really everything we need to change. So that's it. Let me try and rerun this and make sure that it actually works. Right. So let's see. I perhaps forgot to remove the wait clip. So wait clip. Yeah, we need to remove those two since we're now doing it with the gradient penalty instead. And one thing I realized is that we want to set this affine to true in the instance norm. And this is just so that it has learnable parameters. All right, so I haven't trained this for very long. As you can see, it hasn't even gone an epoch or close to it. But as we can see, the training is definitely working. And if you want for fun, then train it for a longer time and then see what it actually converges to. But that's it for this video. Hopefully you were able to follow along and implement WGAN and WGAN-GP and understand sort of the rough intuition of why it works.